And we're back. Can anyone hear me?
Yep, you sound good to me.
Oh, good. Hey, Charles, since you can talk, I'm going to, when I share my PowerPoint slides, I'm going to maximize that, or rather go into presentation mode. And can you let me know if it gets, if one side of the slide gets cut off, or let me know. I'm trying to track this issue down. I can't debug this because it won't allow me to have two logins into the Collaborate session. So it's not like I can have, you know, one machine that's logged in and presenting and another machine logged in and viewing.
Yeah, that's no problem.
Okay. Okay, there we go. Okay, so that should be maximized, and you should be able to see.
I don't see you. Oh, there it is. Yeah, no, it's still cut off.
Okay, well, I guess Collaborate just.
Maybe they have like a max resolution or something, because you've got like pretty big monitors, as I recall.
Yeah, that's a 4K. That's pretty. Okay. All right, that's okay. I can. It makes sense they wouldn't have tested this software at any point.
Not very ultra, is it?
No. Okay. Well, all right. I'll just leave it like this. Hopefully, if I just maximize, is it getting cut off now, or?
It's close. I think it's okay.
Okay. Okay. Maybe it's not the resolution then, because that was.
Yeah, it's good. It's good now.
Okay, so so everyone knows, I thought this was interesting. I got an email a couple days ago from the department chair with the fall course schedule, and I'm teaching 611, and I noticed that it's set up right now to be the way it was 2 fall semesters ago. So it has 2 sections. They're both in-person lab sessions. There are no virtual sessions. So I'm kind of excited about that on one hand. It means everything will be presumably back to normal in the fall, although I'm kind of concerned because if even one student wants to take the class virtually, they technically do not have that option at this point. Also, it's going to feel strange being back in the lab with everyone, but I think hopefully assuming that happens, we'll get used to it again. But I just thought I'd point that out. I don't know if all the courses are like that, but my course is going to be, we're all going to be on top of each other in the lab, breathing down each other's necks again, like we used to in the old days. So that's the plan. Okay, so a couple announcements here. So one, I've got quiz 4 is posted on Moodle on Blackboard. It will go live after class, at 5:10 p.m. today, and it will be due before class next Wednesday. So you have to take it by 3:55 p.m. on the 10th, Wednesday the 10th. The quiz is covering real-time scheduling. I might be able to get through all that material today. Hopefully I do. If not, then I'll finish it up on Monday. But I'm still going to give you about 20 to 25 minutes at the end of this lecture so you can go in and check it out and open the quiz and start thinking about it, because there's no time limit or anything. So you can open it and take a week to answer it. The other thing I wanted to quickly go over is Lab 2. Remember, we assigned Lab 2 on Monday. It's due on the 19th by midnight. So you have the rest of this week, next week, and the week after to take it, or to do the lab and to submit it. The lab is about reading, or actually decoding SPI transactions. There are 3 tasks or 3 parts to the lab that are meant to be done incrementally. The first part is decoding what I call simple read and write transactions, which are transactions that read or write 1 byte, and they have the cpool and cfa are locked down to 0. The second part is to decode streaming or multi-byte read and write transactions, again with cpool and cfa set to 0. And part 3 is to decode simple and streaming transactions with arbitrary cpool and cfa values. So last time I went through some examples of this, I mentioned, now you might say, gosh, boy, have you gone over SPI a lot. Yeah, that tends to be a topic we hit quite heavily in this class. But I want to emphasize that SPI is only defined as a standard for doing exchanges, not transactions. So whenever you build a transaction level protocol, like for doing reading and writing, there's no standard for that. It depends on the vendor. And so for Lab 2, Charles has developed a way to do the transactions, and it doesn't necessarily match up to anything that would be, off the shelf. It's something that we kind of made up, and it's pretty typical that when you do SPI, you have to look up in the data sheet for the peripheral, what the dialect is of the transaction level protocol, or how it works. So so in this case, when you do the simple transactions, there is 2 exchanges. In the first exchange, bit 1 and bit 0 are used to denote whether it's a read or write and whether it's a single byte or streaming transaction. So bit 1 is 0 for read, 1 for write. Bit 0 is 0 for single and 1 for stream. And then after that first exchange, then it's the data is transacted. I think that should be fairly straightforward. So when you do a read, it's MISO. When you do a write, it's MOSI, is used for the second exchange. Now the part that I screwed up last time, because I missed a detail when I was reading through the lab sheet, is that when you do a streaming read, the number of exchanges is going to be actually 2 more than the number of bytes that are exchanged as part of the transaction. There's kind of 2 overhead exchanges that are done at the beginning. The first one is the address and the flags, as was the case with the single byte transactions. But then there's a second byte that's sent from the master to the slave, that gives the number of bytes that are transacted for the remainder of the transaction. So you have to be. I just want want you to make sure everyone's understanding this. It's described in the lab sheet, but I want to make sure I didn't confuse you by having missed that detail when I was explaining this on Monday. So here's an example. I regenerated this waveform, so it is now consistent with what's in the lab sheet. So in this case, the first exchange gives an address in 6 bits, which is most significant bit to least significant bit for the bit ordering in the address. And all the data words are also set in that bit order as well. So that's convenient because you can read it from left to right. So there's a 6-bit address, and in this case it would be 2 and 4. So you see the 2, 4 down here in the output. This is the output message that your program should print. And then bits 1 and 0 are the flags. So the first one says 0 because it's a read, and the second bit is 1 because it's a stream. And then the next exchange, the next byte sent from the master, is the length of the stream, or length, the stream length is in this case 2. And then you have 2 additional exchanges in which the master is sending 2 bytes. In which the slave is sending 2 bytes back to the master because it's a read. And those bytes would be 0F and B0. And so in order to do a stream of length 2, you have to do 4 exchanges. 4 bytes have to be exchanged as part of the transaction in order to do a stream of length 2. Okay, and then likewise for a, I should say write. Right. For a streaming write, the write flag is set to 1 inside of the header, the header byte, the first byte that's exchanged. And again, there's a 2 in the second byte that's exchanged because this is also a write of length 2 bytes. And then there's 2 bytes that are sent from the master to the slave, B0 and 7E. if you convert the binary to hex from from left to right, most significant to least significant. And so the message printed there is write stream 34, which is the address, B07E. So these messages are the decoded, basically a decoding of what happened inside the signal trace file. And then I updated this slide. So I had some text on two of these waveforms, I think, that said that it generated from they were least significant to most significant, so I deleted that. I don't want to confuse anyone. As I mentioned earlier, all of the data in this lab is sent most significant to least significant in terms of the bit ordering. So I just changed this to show there's 4 combinations of CPUL and CFA, and so I showed the rows are CPUL and the columns are CFA, 0 and 1. So like, for example, this guy in the lower right hand corner is CFA 1, CPUL 1. And I think this slide might help you when you're debugging your code, especially in part 3, in order to figure out which edge of the clock to read the data on. So that's why I wanted to make sure that I had all four waveforms there. Okay, so if you have any questions, feel free to post them. I updated these slides on Dropbox, so hopefully this together with the lab description or the lab sheet will make it pretty clear what we want you to do. I think Charles mentioned in the last lecture that his reference solution was fairly short. So these programs are the programs that I tend to assign that students write in my courses tend to be pretty short, but they can be tricky. It's not like you're not gonna, it's not like 240 where you're writing long programs. These are usually pretty short in terms of lines of code, but you have to be careful when you're writing them, because it's if you're off by a half clock cycle here or so, it'll change the result. Okay, all right, now I'm gonna switch back to the lecture. Okay, so last time we also talked about real-time scheduling. So scheduling is an operating system concept, but even if you don't use an operating system, or your operating system is kind of a thin, kind of a library-based operating system, like like they have on some embedded processor vendors will ship. Your code may still be very low level, but you may have something that's managing tasks and managing, multiplexing the CPU, basically. So, scheduling is this idea of deciding what the CPU is doing at any given time. It takes all the workload, and it decides which task is going to be running on the CPU at any time. In real-time scheduling, we're worried about making sure that all tasks meet a deadline that's associated with each task. The first issue with that is determining what the maximum runtime of a task would be, or the worst case execution time. And so this is a difficult problem in and of itself, because there's a lot of uncertainty in processors. You've got memory access. You probably remember from 212 that there's memory access time is something that is when you can generate average memory access time, but the actual memory access time is a random variable depending on the performance of the memory system and other things that are happening. There's also interrupts, exceptions, and there's also data-dependent behavior in code. So basically, the only way to really determine the worst case execution time is to look at the execution time as a random variable and model it that way. So I gave you an example last time where we had these 10 observed runs of a task and the corresponding execution time in milliseconds, and then I asked what's case execution time at a 99.9% confidence, assuming a single normal distribution. So in that case, you're considering all of these runs to be part of one distribution. a normal distribution or Gaussian distribution. So this is kind of like a black box way to evaluate this, because you're not considering anything about the internals of the task, just what its execution time was. So in this case, the mean, you calculate the mean is 20.5 milliseconds. The standard deviation is 9.2. And so your worst case execution time at 99.9% confidence is 20.5, which is the mean, plus 3.09 times the standard deviation, which is 9.2, which is 48.9. And that's a pretty, that's a pretty high value compared to these values that you observed. On the other hand, it may be the case that the execution time is comprised of two random variables depending on the control path followed through the task. So this is kind of a glass box sort of way to measure this, where you see, well, there's basically two different modes of the task, or there's two different things the task may do when it runs. And based on that, I can calculate two means based on which of those two modes or which of those two paths it followed, and two standard deviations. And then I can just calculate the maximum of the worst case execution times of both of those separately. So in this case, out of the 10 runs, I say assume the first and second 5 measurements are generated from two separate control paths. So you calculate the mean and the standard deviation of the first 5 and the second 5 times. And then from there, you actually end up with a 16.9 and 38.0 as your calculated worst case execution times for each of the control paths. And so you just take the maximum of those, which is 38. Now you're comparing now 38 versus 48. This is a much tighter approximation, so that's, now I didn't ask a question like this on the quiz. I forgot to put one in like this, but make sure that you understand how to calculate these, because I'll put one of these types of questions on the exam. Okay, and then so what about scheduling? So tasks can be ready to be executed and waiting to get time on the CPU, or they can be asleep, meaning that they exist, but they're not requesting access to the CPU, or they can be currently executing. We're going to start out by assuming that the CPU can only execute one task at a time, because there's only one CPU core. So let's assume now that we have 4 tasks, each has a different computation time, or worst case execution time, and a different deadline. So now every time I give you a list of tasks, I'm always going to give you the time, the execution time, and the deadline associated with them, kind of as a pair. And so there's 24 possible schedules. It's n factorial, 4 factorial. And so of those 24, only 2 of them meet deadlines. So for example, this guy, number 2, we run task 1 first, then task 3, then task 1, then task 2. And as you can see, all of those complete before their little red lines that denote the deadline. All the other ones fail except for number 8. Number 8 is task 3, task 4, task 2, and then task 1, then task 2. So what's special about those? Well, it turns out that the first number 8 was when we, I did a full enumeration in this case, but number 8 was when we gave priority to the task with the earliest deadline. So in this case, we ran task 3 first. Why? Because task 3 had a deadline of 35 milliseconds. That was the lowest or the earliest deadline of all of the other tasks. Then we ran task 4, which was 37. That was the next lowest or next soonest deadline. Then we ran task 1, which was 76, then task 2. So that was that seemed to be a good approach. The other schedule that worked was the least slack first. Slack would be the difference between the deadline and the execution time. So I had to recalculate those values here. So Boy, this would have been a good quiz question too, actually, now that I think about it. But I didn't ask one like this either. But you calculate the least slack. So the one with the least amount of slack, once again, was 4, which was 37 minus 20. So we ran task 4. Then we ran task 3. Oh, sorry, actually, last time we ran task 3 first, then task 4. Now we've switched it up. We're doing task 4, then task 3, and then task 1, and then task 2. So task 2 had the most slack, 84 minus 6. So those two approaches worked. Another approach would be to run the shortest task first, which we actually tried. We tried them all. Task 2 was the shortest task. We ran that first. Then task 3, then task 4, and then task 1. And this is shortest task in terms of execution time. But that didn't work. It actually caused task 4 to miss its deadline. So you don't have to run task 4 first. You can run it after task 2, but you can't run it after task 2 and 3. It'll miss its deadline. So that one didn't work. So this was kind of just an ad hoc, approach. I just fully enumerated those things. But it's when you have a real-time operating system, it's much more common to have the tasks be periodic as opposed to running one time with a deadline, because a deadline doesn't make a whole lot of sense when you're just running tasks unpredictably or starting from a certain reference point. It's more common that when you run tasks that have deadlines, it's because you're doing a control algorithm where you're having a task read some input, make a control decision, and then send an output to a plant and have that done at a fixed interval. So a periodic task set it looks very similar to the ones we looked at before, where you have a computation time and a deadline, except the deadline is actually also the period. The period meaning that after however much time is specified by the period, the task wants to run again, and it has to finish before the next time it's run. So these tasks are periodic. So this is the same data that I showed before, the same 4 tasks, but in this case, these are, instead of deadline, I've labeled this column period. So task 1 will reissue to run and complete every 76 milliseconds, and task 2 has to run and complete every 84 milliseconds, and so on. So this would represent, the sample time. If you're doing a control algorithm, this would be your sample time. So remember when we looked at the Z transform and the Tustin, we did the Tustin transform and we had to pick a T value. This would be your T for these tasks. And so if you miss a deadline, it could mean some serious problems. It could mean that the control algorithm is not able to stabilize the plant, which is something you don't want. So you want to make sure that you can run these tasks whenever you want, as long as they run and finish within their period. So each task has an execution time again of I call it T of I. The notation is different depending on what you're looking at, depending on the textbook or the paper you're reading. But in this case, I'm going to say T is the execution time, T of I or T of K, and the period is P of I. Now, the other thing that's important that you generally have with periodic scheduling algorithms is that you generally will assume that the tasks the tasks are preemptible, meaning that a task can interrupt another task if it has higher priority, and generally that's going to happen whenever you hit the beginning of a period of a task, and if that task has a higher priority than another task, then the task with higher priority will seize control of the CPU and cause the one that it preempted to have to wait. And that can happen when a task initiates, or it can just happen. It doesn't even have to happen when a task initiates. It could happen at any time. But this is if you don't have preemption, then it makes it very difficult to meet deadlines. There is some stuff about there are some algorithms for doing non-preemptible scheduling, but the preemptible case is the easier case, and it's the more common one. So what you can calculate now is utilization, which is if you take your tasks and you add up the ratios between their their execution time, and their P's, and you add those up, you can calculate the utilization of the processor. So if you take the ones that I gave you and you assume now that they are periodic, because again, before they were not periodic. So before, like after I got done running this task, or after the task deadline, it didn't like task 3 after its deadline, it didn't want to rerun again in the previous example. But now in a periodic case, they want to run again every period. And so if you calculate the utilization of this task set, which would be 40 over 76 plus 6 over 84 plus 14 over 35 plus 20 over 37, that adds up to be 1.5383, which would be basically 153% utilization, which means that it does not matter how advanced your scheduling algorithm is. It's not possible to schedule this on just one processor, because you just have 100% of your time. So this will never be schedulable, and the operating system would have to recognize that, and if you tried to give it this task set, it should reject it, saying that's impossible, can't be done. So two of the most common approaches for doing the scheduling are earliest deadline first, which we talked about in the previous example, and rate monotonic scheduling. Earliest deadline first is abbreviated EDF, and rate monotonic scheduling is abbreviated RMS. So the earliest deadline first is pretty self-explanatory. You want to schedule the task that has the earliest deadline first, which means that you're basically prioritizing any task who has that corresponds to the next upcoming deadline. So at any time of all the tasks that could be executed, you want to use the one you want to assign the one to the CPU that has the earliest deadline, which is what I just said. Makes sense. RMS is a little different. In this case, you're going to schedule tasks that have the shortest period first. So at any time, you're going to give highest priority to the task with the smallest period, and the next highest priority to the one with the next smallest priority. Okay, and as I mentioned, these are both assuming preemptible, meaning that at any time you have a task that is in the ready state that has a higher priority than the task that's in the running state, then you're going to change which task you're running. Okay, so let's talk about earliest deadline first. Basically, if you calculate the priority, and if a lower priority value means higher priority, which is a little counterintuitive, but if you calculate a priority value of task K, you can calculate it as the period of that task K minus the current cycle modulo the period. So it basically, whatever value you get, whichever of these priorities is the lowest, is the task that you want to schedule. So that the equation there is a little confusing, but the reason why you have to do it that way is because you don't really have a deadline per se. You have a deadline, but the deadline is the period. But when you're trying to figure out which deadline is closer, you need to take into account where you currently are in time relative to all of the end of all the periods of all the tasks that are currently ready or running. It's kind of I don't think I explained that very well, but the point is that you have to find out of all your tasks that are either running or ready, which of those has the closest deadline in terms of end of its period. So it turns out that if you do that, you can then schedule any task set as long as the utilization is less than or equal to 1. So here's an example of 3 tasks, 10 milliseconds, period 40, 15 milliseconds, period 50, 5 milliseconds, period 20. This gives you a utilization of 80%, and then I'm showing the schedule there down below. Now you might say, well, okay, well, that's an easy value to calculate. And the scheduling algorithm works pretty well because it basically guarantees that you can schedule anything as long as it doesn't exceed 100% utilization. So that seems, problem solved, moving on. But the problem is that EDF is not a practical algorithm to deploy because for a variety of reasons, but the biggest one is that the priority is a function of the current cycle number. That's the problem. That makes it almost impossible to actually implement this because it means that you have to continuously reevaluate the priority of all the tasks at every moment in time. And the minute one task that's ready has a higher priority than one that's running, then you have to context switch. So number one, that's going to mean that you have to, you could be doing a lot of context switching, but also it means that you have to constantly reevaluate all those priorities. And also it means that if you have a mixture of real-time tasks and non-real-time tasks that have a fixed priority, it doesn't work, then the whole thing will break. But the biggest issue is this idea that the priority is a function of time. And I can tell you, it might not sound like a big deal, but I can tell you from experience when I implemented this myself to generate these timing diagrams, it's really hard. It's tough. It would be much easier if these tasks had fixed priorities. So you could just, you wouldn't have to continuously change the priorities. You only have to continuously worry about changing which task is running at any time. So that's why we have rate monotonic scheduling, which is much more practical. So basically, rate monotonic is where you set the priority of each task to just equal essentially the period. So lower periods give higher priority. And so this way, because the priority is not a function of the current time, it's just a fixed static priority. And all you have to do is just basically just monitor the set of tasks that are ready and running and make a decision about which one to run. So basically you only have to reevaluate which task is running whenever there's a new period, whenever a new period starts of a task. Okay, so let's go back here. Let me step back a minute and let's look at this timing diagram for EDF first. So in this case, you'll notice that task 3 was, if you look from the very beginning of time here, task 3 ran first because it has the we're starting out with all the periods lined up, or all the tasks are kind of aligned. And so task 3 has a period of 20, so obviously it's going to have the earliest deadline, so we run that first. Then we run task 1, which had a period of 40, and task 2, which had a period of 50. So when we start out, everything is nice and easy. We just look at basically the period and make our decision from that point. But then things get more complicated, because when task 3 ends its period, we are now at time 20, right? So now we have to decide, what are we going to do? Like at that point in time, task 2 is running, but we're going to have to seize control of the CPU from task 2 and give it back to task 3, because task 3 is actually going to be a higher priority than task 2, even though task 2's deadline is approaching. Its first deadline is approaching, but we're now on our second deadline of task 3, and it is still closer than the first deadline of task 2. So we're going to run it. Now you might say, oh, wait a second, what about task 1? I mean, task 1 had a period of 40, and task 3 had a period of 20, and so task one in the second period of task 3, you're going to have the same deadline as the first period of task 1. True, but task 1 is already finished. We completed it. So task 1 is sleeping at that point. So there's no reason to run task 1. We got to run task 3. And then once task 3 is done, we go back to running task 2, and then we don't have to worry about anything until we get, task 3 starts a new period, at which point task 1 and 3 are both ready, but task 1, it doesn't have to have a deadline until 80, and task 3 has a deadline at that point of 60, so we run task 3 and so on. So if you go by period for each one of these guys, task 1, you can see it meets all its deadlines. Task 2, it meets all its deadlines, although it gets preempted on the first period and on the second period, but not on the third period. And it does again on the fourth period. So you can see that when these guys get out of sync, there's kind of from period to period, they exhibit different behavior. Task 3 always, is always the highest priority and always meets its deadline. So that's fine. Now we get to rate monotonic scheduling, and now we look and we see, well, okay, task 1 or task 3 had the highest priority and it runs. Task 2 again gets preempted by task 3 whenever it issues, and then task 1 generally is going to be the second highest often, and they all meet their deadline. So it looks like everyone met the deadline. So this schedule looks like it worked out, and that was with a utilization of 80%. So how about another example where we have also 3 tasks, but this time we're gonna make things a little tougher for these algorithms. So we have 3 tasks in this example, but now we've got 4, 10, 3, 12, and 5, 15. This gives us a utilization of 98%, 98.3%, and we run RMS and EDF. And if you look at the RMS schedule, we look at task 1, it seems to be, well, it's the highest priority, so it pretty much just runs at the beginning of each one of its periods, so no problem there. Task 2 is going to be the second highest priority, so it pretty much runs as long as task 1 is finished, it will run next. And as you go from period to period, it finishes. You can see that in period 1, 2, 3, 4, 5, in the 5th period, it gets preempted by task 1, but it still finishes well ahead of its deadline. But then you get to task 3, and it met its deadline the first period and the second period. But then we get to the 3rd period, and suddenly it misses its deadline. It ran right into its deadline there. It didn't happen until the 3rd period, though. It's kind of odd. So the RMS schedule failed. The EDF schedule was fine. No one met their deadline. No one missed their deadline. And that makes sense because, like I said, as long as you're under 100% utilization, EDF will work. So how do we know when RMS is going to work and when it's not going to work? Well, there's a schedulability test for that. Now, when I was in graduate school and I learned about this, they actually had a different schedulability test, because it turned out that the schedulability test just says that if the schedule passes the test, I guarantee you that it's schedulable. If it doesn't pass the test, then it doesn't mean it's not schedulable. It means it may not meet the deadlines. So it's the only thing you can guarantee is that it will be schedulable if you pass the test, but if it fails the test, you don't know whether or not it will be schedulable or not. Well, when I was in grad school, basically the RMS schedulability test said that as long as your utilization was less than 69%, which was a value that was derived mathematically, then it was guaranteed. But now they have a tighter bound. So this has actually changed because the understanding of the scheduling is a little bit better now than it was before. So of course, unfortunately, I changed the notation. I switched up the notation here, so I'm gonna actually change that back so it's not confusing. Yeah. So yeah, I'm gonna update this. Sorry, execution time is T and period is P. Okay, so execution time is T of K, period is P of K. But instead of calculating the utilization, which is a summation of the ratios of execution time to period, the latest RMS test is where you multiply together 1 plus T of K over P of K for all of K. And if that product is less than or equal to 2, it guarantees that the tasks are schedulable under RMS. Now, again, if they exceed 2, if that value exceeds 2, it's greater than 2, then that just means that it may or may not be schedulable. But there's no way to know. So, in our previous example, the first example I showed you, we had 3 tasks with 10, 40, 15, 50, and 5, 20. That was the one I showed you. That was this one, right? That was the one, this one. Yeah, so this one had our utilization of 80%, and then I ran, several periods of each task, right? So I had 1, 2, 3, 4, 5 periods of task 1, 1, 2, 3, 4 periods of task 2, and 1, 2, 3, 4, 5, 6, 7, 8, 9 periods of task 3, or sorry, actually 10 periods of task 3, and it appeared, at least for that interval of time, no one missed their deadline. Now but see, of course, that's no guarantee that you won't miss a deadline in the future, right? Just because I ran, I did a little test of these guys, and no one missed their deadline, that doesn't really tell me anything. But it looked like everything met, at least, in this example. So if we run the RMS schedulability test on that, the way you do that is 1 plus 10 over 40 times 1 plus 15 over 50 times 1 plus 5 over 20, and you multiply all those together and you get 1.95. So it turns out that according to that test, because 1.95 is less than or equal to 2, these tasks will always meet their deadlines under RMS. However, if we take the second example, which is the one I did here, okay, where I showed task 3 missed its deadline. This is the more aggressive example here, 4, 10, 3, 12, and 5, 15. I calculated the schedulability bound here, and it's 2.33. So you can see that this one exceeded the limit of 2, and so we knew just from calculating this just from doing the schedulability test, that the second set of tasks here are not schedulable under RMS. And again, I was able to see that fairly quickly after actually trying to do the schedule. Again, though, it didn't happen until we got to the third period of task 3. So it wasn't evident at the beginning that this was a doomed schedule. But luckily it happened fairly early on. But again, we wouldn't have had to do that if we just calculated the schedulability test. Okay, now there is a couple caveats to that. The first caveat is that RMS works really well and can achieve 100% utilization, or can schedule without any task missing a deadline up to 100% utilization if the periods are mutually harmonic, meaning that if you were to sort the periods from smallest to largest, that each period would be a multiple of the one that is below it in that list. And so here's an example of that, where I've got a task set that's 10, 20, 10, 40, and 20, 80. That actually adds up to a utilization of 100%. And I show it here, and well, at least it doesn't miss any deadlines here, but it's pretty obvious that there's a pattern that repeats. These guys don't go out of sync. So there's a repeating pattern here, and you can tell that no one's gonna miss their deadline. Okay, so that's basically all single processor scheduling. Now let's talk about multiprocessors. So as I mentioned, most cyber physical systems have one processor. At least now they do. Some might have multiple processors, and you may want to do real-time scheduling on multiprocessors. As you might imagine, that's more difficult than a single processor, and this is still an open problem. Basically, no one has a perfect solution to this. There's whole conferences devoted to solving this, as well as other similar problems like RTSS, the Real-Time System Symposium. So there's a couple approaches though that you can take. One is called partition scheduling, which is where you assign all your tasks to a specific processor. So you decide ahead of time which tasks are going to be executed on which processor, and then you just schedule them using a uniprocessor schedule, right? That makes sense. I mean, it seems reasonable to me. Except the problem with that is that if you're scheduling, if you have n tasks and m processors, there are m to the n ways to do the assignment. So it's NP complete to figure out how to do the assignment. So that obviously is not going to scale very well. Of course, it would. I mean, it's feasible for a small set of tasks, but not feasible if you have a lot of tasks. Now you might say, well, how often do you have a lot of tasks? Well, it depends on the application. It depends what you're doing. If it's a drone, there's a lot of tasks. There's a lot of things you need to control, or any other kind of autonomous vehicle. Another approach is global scheduling, where you have an algorithm that will assign any task that's ready potentially to any available processor, and that's kind of what you're kind of used to with multi-core systems, how they usually work. They're symmetric multiprocessors. You can have any task go to any processor. So there's in terms of global scheduling, there's a few different variants of that. One of them is called rate monotonic first fit periodic scheduling, which is a mouthful. But the idea with this is that you assign so basically what you're trying to do here, let me back up a minute. The objective here is to figure out how to assign ready tasks to processors without fully enumerating every possible way to do it. You don't want to do that, because that would reduce down to partition scheduling. So global scheduling, basically what you're doing here is trying to develop a greedy algorithm that will pick a processor in a way that you can get good utilization. So now, without going through the whole proof of this, the whole thing is schedulable if you can guarantee, again, you can guarantee schedulability if it passes the test. If it doesn't pass this test, it may or may not be schedulable. So what's the test? Well, basically you add up all of the, did I screw that up again? I'm sorry. It should be T of K over P of K, time over period. So you add up all your utilizations, or you calculate the total utilization. Okay. Now remember that when you have tasks, you're ideally, as long as the utilization is less than n times 100%, where n is the number of processors, ideally you can schedule that. Now, of course, in practice, as you can probably imagine, you can't. Just like with regular RMS scheduling, you can't necessarily schedule even if your utilization is less than 100%. For a single processor, or in this case, multiprocessor, it would, like if you have two processors, it would be 200%. But the best test right now, as far as I know for this, is as long as utilization is less than m, which is the number of processors, multiplied by 2 to the 1/2 power, square root of 2 minus 1, okay, which is, about 0.4, because the square root of 2 is 1.41. So as long as the utilization is less than 0.41 times the number of processors, then it's schedulable. Okay, so what does that mean? So let's look at an example again where you have 4 tasks with the following execution times and periods. So on one CPU, the utilization here would be 76.5%. And if you calculate, if you do the single RMS bound, or test rather, you'd have 1 plus 2 17s times 1 plus 2 19s plus, or times 1 plus 5 21st times 1 plus 5 or 7 23rds. You multiply those guys all together, you get 1.9949, which is just under 2. So you could schedule these on one processor. Now, if you can schedule them on one processor, I mean, I would hope I can schedule them on 2 processors, right? Because I'm adding more hardware without adding any more workload. So the answer, can you? Well, interestingly enough, if you take 76.5 and you divide it by, well, so actually, the bound here would be 0.41 times m. So the m is 2. So you want to make sure that the utilization is less than 82, right? And it turns out that I think I screwed this up actually. That should be just, it's not divided by 200. It's just 76.5 as I calculated before, and it is less than 82%, which is the bound, right? So what does this mean? What am I saying? So for this rate monotonic first fit periodic scheduling, you calculate the schedulability test a little bit differently than you do for a single processor. For a single processor, you do that thing where you do that product, right? You multiply a bunch of things together, basically 1 plus the ratio of execution time to period for each task. You multiply those all together, and you check to see if it's less than 2. When you go to the multiprocessor algorithm, the multiprocessor version of RMS, which is the rate monotonic first fit, well, this is one, I guess this is the first fit periodic scheduling, so it's one of the RMS versions as applied to multiprocessor. You don't multiply the numbers together, you just go back to regular utilization, but you compare it to a bound, which is 0.41 times the number of processors. So in this case, the utilization was 76.5, and because that is less than 0.82, no problem, you can schedule it, right? So yeah, I had a typo here too. Okay, so in another example, let's say you have these tasks, so 3, 17, 2, 19, 5, 21, 6, 23. These are your new set of tasks. And on one CPU, well, the utilization in general is 78%. So on one CPU, when I do the schedulability test, which is the product test, right, the result is 2.03, which exceeds 2. So that means that this probably, well, it fails the test. So this may not be schedulable on one CPU, right? But then if I go to 2 CPUs, I note that the utilization again, as originally calculated is 78%, and it is less than 0.82, which is the 0.41 times 2. So this thing should, or actually it's guaranteed to schedule on multiple CPUs. So this is an example where it won't schedule on one, but it will schedule on 2 CPUs. Does that make sense? Hopefully. Sorry for the typos there. I had that originally. I had it normalized to 200%, but that is, you don't need to do that. I was making things more complicated than they need to be. It's just the original utilization compared against 0.41 times the number of CPUs. So that's the idea. Okay, well, I'm going to go ahead and I said I would give you at least 20 minutes to take a look at the quiz and start working on the quiz. The quiz has just 10 questions on it. And so I'll give you some time to do that now. So I'll end a little early. I'll finish the lecture up on Monday. I just have one more scheduling algorithm to show you, and that would be the kind of the EDF version of the algorithm for multiple processors. And then we'll move on to our next topic. Any questions? Okay. Okay. Okay, great. Well, if you have any questions about the quiz or if you see anything suspicious, let me know. If there are any, issues there, I'll be sure to fix them and send an update. And in the meantime, if you have any other questions about the lecture, let me know. Oh yeah, sorry. Oh yeah, that's a good point. I should have opened the quiz earlier than the end of class. Sorry, I'll do that right now. Sorry about that. I just reflexively set it to 5:10, but okay, okay, that should fix it. Sorry about that. Thank you for bringing that up. Timing, yeah, open the quiz. It should be open now. Okay. Okay, great. And like I said, I updated the slides on the website. I've made a few changes, obviously, today, and I'll keep the slides updated on the website when I post. I'll update them when I post the lecture on there. Okay, thank you guys, and I'll see you on Monday.